Everyone. I will be starting with the session now. Dear authors and
Hello,
investors. Hello, ma'am.
hello, Miss Dimahi.
Yes, ma'am. Do you have to say something, ma'am?
They might please proceed with the welcome remarks.
Yes, okay. Dear authors and invited guests, welcome to this technical session 6D. I am Dimahi Patel, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you to the 10th International Congress on Information and Communication Technology, London, United Kingdom. This 10th edition of the conference is being organized in the hybrid mode. The physical event was held yesterday in London, and the virtual event is being held through Zoom from 19 to 21st February 25. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we will have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for the question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Now, just before we start the session, I would like to introduce you all to the chair of this session. We have with us Professor Renata Mekovic. Professor Renata Mekovic is an associate professor at the University of Zagreb and the head of Department for Information System Development and member Department of Computing and Technology. She is a researcher, lecturer, and IT expert. Her research interest is in the field of privacy and personal data protection, e-service quality and evaluation of e-service quality, and e-service users' perception of privacy. Ma'am, I would request you to share a few words to everyone present here today.
Hello to everyone. So I'm Renata Mekovic and I will be the session chair in this topic. I'm looking forward to a productive and informative conference. We have a great lineup of speakers and topic, and I invite everyone to share your ideas with us.
Yes, ma'am. Thank you so much, ma'am. Now we will be beginning with the presentations. First up, we have Dominic presenting a study on continuous learning system for detecting anomalies in daily routines using an autoencoder. Dominic, are you here with us?
Yeah, I'm here. 1 second. All right, you should see my screen, right?
Yes, sir.
All right. Then, hello everyone. My name is Dominik Giebitz from the Frankfurt University of Applied Sciences. And in this presentation, I would like to give you an insight into the project for a continuous learning system for detecting anomalies in daily routines using an autoencoder. Let's start with a quick look at the agenda. First, I would like to give you a brief introduction to the background and motivation behind this project. Next, I will talk about the objective, the general approach, and the method. And after that, I will give you an insight into the procedure and show some results. And finally, a short summary and a few words about the future plans. So the demographic change is a well-known topic, and where the average age is rising, and with it, the number of people requiring care, and also the number of skilled workers that are needed. And elderly people who live alone are at risk of accidents going unnoticed, and such accidents can not only lead to health problems or even worse, but can also affect their general quality of life, maybe due to the fear of another accident that could happen. And that's where technical assistance systems can provide support. On the one hand, by recognizing emergencies such as faults, and on the other hand, such systems can detect general changes in daily routines, which enables to take preventive measures before accidents happen. And that's exactly an aim of the project. We want a system that can recognize changes at an early stage and inform relevant people before something happens. And this should help to maintain the health of a person and at the same time provide a sense of security to them. And we want to achieve this by developing a system that constantly learns the individual normal behavior of the person and recognizes deviations from this using anomaly detection. And by constantly observing gradual changes over a longer period of time should also be recognized. And we want the system to work purely local to preserve data privacy, so no cloud or similar. For the development and validation of our approach, we use publicly available datasets of people living alone. And based on sensor triggers from motion sensors, features are extracted and the person's daily routine can be reconstructed. And the features we are extracting are always dependent on the time and the location of the person. So one feature is the time spent in each room at each hour. This feature shows, for example, unusual stays at certain times. Then we have the activity time as a feature, which gives a general insight into the movement, time, and frequency. And then we extract the number of room entries for the respective hour. This is to recognize frequent walking back and forth, for example. And these features will be used to learn the normal behavior of a person. And to learn this, we use a neural network in the form of an autoencoder. And to keep it short, the core principle of an autoencoder is to compress the data and thereby learn the essential informations autonomously. And after that, the neural network attempts to reconstruct the original data from this compressed representation. And if the input data corresponds to that what has been learned before, the network reconstructs the data without major errors. And otherwise, it indicates an anomaly. And the aim is for the system to adapt to a person's individual routines. And to achieve this, the system must be trained from scratch and does not allow a generalized pre-trained network. And also this system should be usable in any previously unknown environment. So the general procedure of the system is as follows. There's a warm-up phase for the first few days. During this time, the system is only learning and does not check for anomalies. And also the system extracts maximum values for every room individually, which are used for normalization of the data. After this warm-up phase, the next steps are the same for every day. The data is first normalized as the features are in different data types, such as the time is in seconds and the number of room entries is just a low value. Then the normalized data is fed into the neural network, which then attempts to compress and reconstruct the data, just as I mentioned before. And with the reconstructed data, we can calculate the error, which then indicates whether it's an anomaly or not. So it means that if the average error exceeds a certain threshold, it means that the deviation to the learned normal behavior is too large and the day is detected as an anomaly. And otherwise, if the day corresponds to the learned normal behavior, it is then learned to further improve the system. And at the same time, the maximum values of each room are updated if necessary. So several tests were done using this approach I just described. These tests were based on a publicly available data set, which is based on the data of an apartment with 6 rooms or defined areas. And all days were classified as normal or abnormal using statistical methods and a manual review. And to investigate the effects of the capacity of the hidden layer and to find a balance between the underfitting and overfitting, the number of neurons in the hidden layer was tested with 3 different sizes. And depending on the number of neurons in the hidden layer, the number of training days was varied slightly. That's because a higher number of neurons enable faster adaptation to new or unknown patterns, which means that fewer training days are required and overfitting is avoided at the same time. And in addition to that, 3 different initial values or maximum values for the normalization of the 3 features were tested for each of these sizes. This is to check whether individual maximum values for each room provide better results than standardized maximum values. So in one approach, the normalization values were set to 0, so that the system had to extract the maximum values completely by itself right from the start. And the second approach is to use small initial values to avoid anomalies that might occur if the person spends little or no time in the room during this initial training phase. And in the third approach, the starting values were set to very high values that are never exceeded in the data. So let's have a quick look at results in form of graphs of the anomaly detection with this system. There are 2 daily routines of a person shown on the top. These are showing one of the 3 features I mentioned before. In this case, it's the residence time of all rooms for every hour. So for example, the blue line represents the time spent in the bedroom, the orange shows the bathroom, and purple represents the living room. And in the day on the left, the person spent around 3 hours in the bedroom that night from around 2 a.m. to 5 a.m. And in the graph on the right, there's a relatively normal daily routine of the same person. Now, the system goes through the data day by day and learns the normal behavior and checks for deviations. And in graphical form, this could look like this. These 2 graphs on the bottom now show the squared reconstruction error for each data point. Or in other words, at which points the system could not reconstruct the data because something else was expected. So in this case, on the left, there are large errors visible in orange. The system expected the person to be in the bedroom, but instead the person stood up at around 5 a.m. and went to the living room, which is unusual behavior in this case. And in the graph on the right, there are also some minor errors visible, which is normal as there are always some deviations in daily routines. Now these are the results of the described test setups. The best results are in each row are highlighted in bold, and it is recognizable that for 42 and for 256 neurons in the hidden layer, the variant with small initial values delivered the best results. So in the middle row of each hidden layer size, and with 128 neurons in the hidden layer, the variant without specified maximum values performed best. And it also can clearly be seen that the worst results were always achieved with standardized maximum values, so the same values for all rooms. This is in the third row of each hidden layer size. And this indicates that the use of room-specific maximum values to normalize the data makes more sense than the use of uniform maximum values for all rooms. And in terms of accuracy, the test results are almost equal, while 256 neurons delivers significantly worse results for the recall, which represents how many of the actual anomalies were correctly detected. The advantage of 256 neurons is that a shorter training phase is required to achieve comparable results. But however, fewer neurons in the hidden layer allow a more targeted feature extraction by the autoencoder during the data compression, which makes the model more robust against strongly varying data. Right, then let's conclude with a summary. The aim of the project is to develop a system that recognizes deviations from the normal behavior through constant learning. And this should enable preventive measures to be taken at an early stage in the future. And currently we can record a person's daily routine using motion sensors and extract various features from it. And by using an autoencoder, we can learn a person's normal daily routine in a previously unknown environment and detect deviations from the normal behavior through anomaly detection. And in the future, the system is to be further improved by analyzing deviations more precisely. And in addition, gradual changes are to be recognized, and the accuracy of the system is to be increased by integrating rules. And that's it from me. Thank you very much.
So I have a question, if I may.
Mhm.
So your results are used in the practice already or not?
No, it's just tested with the data set. It's available online.
Okay. And what do you think results of your project can improve the quality of elderly people? In what segment? What is the benefit of your results and your system for the
So
elderly?
the project is still ongoing. So this is just the current state of the project. But we want a system that detects if there are changes in the behavior in daily routines of elderly people. So maybe if the person spends over time much more time in the bed and moves less and stuff like that, and we want a system that can inform people if something is strange and to so that maybe a caretaker or something can have a look at the person and maybe I don't know, it's a sun drowning syndrome or something like that. That's just that's the idea, and yeah, we with this current state we want to show that we can learn the daily routines of a person. Now the next steps are to have a long time view on the data.
Okay. I wish you good luck with your project and implementation of your work.
Thank you.
Thank you, Dominic. Now I would like to call upon Zhang Xunyang to present his study on contract pre-review assistance system based on RAG and LLM.
Hello, I'm here.
Hello, sir.
Sure. Hey, can you see my screen?
Yes, sir, your screen is visible.
Okay. Then I can start.
Yes, sir, you may please begin with your presentation.
Okay. Good afternoon, everyone. My name is Xiangxuan Yang, and I'm pleased to present our research on a contract preview assistance system based on retrieval augmented generation and large language model. This study conducted with my colleague at Fairchild University in Taiwan, and to improve contract review efficiency and accuracy by integrating AI-driven technique. Manual contract review is a time-consuming and error-prone, while existing AI solution either rely on rigid rule-based system or suffer from hallucinations. Our approach combines LLM large language model with retrieval augmented generation to retrieve verify legal reference, ensuring reliable contract analysis. Contract review is crucial for legal risk assessment, but traditional methods are slow, costly, and inconsistent. AI-based tools offer potential solutions, yet rule-based methods struggle with ambiguity, and a large language model often hallucinates. Our system enhance contract pre-review by integrating RA retrieval augmented generation, which retrieves relevant legal reference before generating risk assessments. This mitigates inaccuracies and improves close classification. Manual contract review is inefficient, prone to oversight, and inconsistent. While AI can accelerate this process, rule-based methods fail to handle complex legal language, and large language model may generate misleading conclusions. By integrating retrieval augmented generation, our approach ensures contract assessments are grounded in verified legal source. reducing error and hallucinations. Our research built on AI-generated legal data, large language model advancements, and retrieval augmented generation-based retrieval. Since contract data sets are scarce, we generated synthetic contracts for training. We employ Llama 3.2 3B, which improve long text understanding and retrieval augmented generation, which enhances retrieval accuracy by incorporating external legal references. Due to limited public contract data, we use AI to generate realistic contracts. This involves data preprocessing, fine-tune GPT-4, and generating diverse contract clauses, followed by manual and automated evaluation. This data set serves as a strong foundation for training our pre-review system. And the next, large language model. Large language model excel in natural language understanding but struggle with long legal text and hallucinations. To address this,
First slide right now. The slide is not moving. Can you please check?
To address this, we implement a sliding window technique, dividing contract into overlapping segments. And any question?
Zhang, can you hear me? Zhang, can you hear me?
Yeah, I can.
I wanted to tell you that your presentation is not showing different slides. We can only see the first slide of your PPT. The title slide of your presentation, we can only see that.
Oh, sorry. Maybe.
Okay, now we can see the LLM slide.
Sorry. Wait. And now can you see next page?
Yes, we can, sir. So don't worry, you can continue with the presentation. Just ensure to change the slides when you reach new information.
Okay, this page is large language model. Large language model is a natural language understanding but struggle with long legal text and hallucinations. To address this, we implement a sliding window technique, dividing contracts into overlapping segments to maintain context. However, large language model alone remain unreliable, which is why we integrate retrieval augmented generation for improved accuracy. Retrieval augmented generation strengthens a large language model by retrieving external legal reference before generating response. Using sentence BERT, our system vectorizes contract clauses for semantic label retrieval, ensuring high precision matching of relevant legal text. Unlike TF-IDF, sentence BERT captures deeper semantic relationships, improving contract clause classification. Our system consists of two main phases, retrieval and generation. In the retrieval phase, sentence BERT search for relevant legal reference, while in the generation phase, the large language model analyzes clauses in context and generates risk assessments. This hybrid approach ensure legally accurate contract reviews. The retrieval phase starts with sentence vectorization, which converts clause into a searchable format. The system then retrieves the most relevant legal reference based on semantic similarity. A sliding window technique is applied for analyzing long contract text, improving retrieval precision. Once relevant legal texts are retrieved, the large language model uses structured prompt to generate risk assessments. The system flags compliant and non-compliant clause, providing detailed explanation. Any flagged risk undergo legal expert review, ensuring reliability and reducing hallucinations. Our experiments show that integrating retrieval augmented generation with large language model significantly improves contract review accuracy compared to using a large language model alone. Our system increased clause classification accuracy from 58.77 to 93.67, while F1 scores reached 91.95 for compliant clauses and 94.79 for non-compliant clauses. The ROC-AUC metrics improved from 0.57 to 0.93, confirming superior risk detection. This study demonstrates that combining RA retrieval augmented generation with large language model enhances contract clause classification and risk identification. Our system improves retrieval accuracy, mitigates hallucinations, and ensure compliance. Future work will focus on optimizing knowledge graph retrieval, integrating multi-model data, and expanding multilingual support for broader legal application. That's all my presentation. Thanks for your attention.
Can I ask a question, please? So basically, I have to give your model some contract, and he will check the contract and say what should be corrected or improved. It is correct? Yeah. But can I do in reverse? So I will say your model, what are the entities of the contract and what is the topic of the contract? Will he produce new contract?
And you say, so you say what is our topic of contract?
I'm asking if I give you information about the topic of the contract and the legal entities who is signing the contract. Will your model produce new contract? Is it possible to do with your model? Or just to retrieve the existing contract? Okay, no problem. We can move to the next presentation. Thank you very much.
Thank you.
Okay, thank you with your presentation. Now, next up, we have Smita Mehendale. Smita ma'am, are you present here? Or are any of the co-authors of Smita Mehendale ma'am present here? Okay, we will move on to the next presentation then. We have with us Yu Zhang, presenting his study on DOVDR, depth estimation and open vocabulary detection for object removal.
Okay. Okay. Can you listen to my voice?
Yes, sir.
Okay. And can you see my present
Yes, sir,
PowerPoint?
your screen is visible.
Okay. Good afternoon, everyone. It's a pleasure to be here today to present our research on the OVDR and deep estimation and the open vocabulary detection for object removal. And my name is Yu Shang, and I'm excited to share our finding on innovative approach that enhancing area image processing for intelligent transportation management and urban planning. And okay, area imagery is essential for urban planning, traffic management, and infrastructure growth. It offers a clear top-down view that help make better decisions. A major challenge is dynamic object like vehicle and people which block road sign, landmarking, and the traffic flow data. This leads to error in automatic analysis affecting navigation, self-driving car, and the traffic transportation planning. To solve this issue, traditional map use static image processing or manual filtering, but these are cost and inefficient for large data set. Generative adversarial network and the diffusion model are used for background reconstruction, but often miss detail like road marking, and this error can cause map mismatching, acting traffic management and the urban planning. Another major challenge is the lack of ability in traditional object detection model. Object detection model like YOLO, RCNN, and SSD require large level data set and mainly learning from ground level imagery. They struggle with area imagery. This happen because of the difference in angle and size and orientation. They also struggle to detect new object limit real world application. To solve this problem, we introduced the OVDR and our approach use zero-shot learning. This let us detect and remove moving object in real time or without extra training. Let me now introduce some of the key technology. Okay. Foundation of our approach start with open vocabulary object recognition or OVD. And OVD is a powerful tool for identifying objects, even if they were not part of the training data. This is especially useful in real zero-shot learning sensory, where the system has to recognize completely new object categories. As shown as in Fig 1 on the right, the processing involves two main components, a text encoder and the image encoder. The text encoder converts description like car or person into a feature space, while the image encoder does the same for image data. These two feature sets are aligned in the shared embedding space, enabling the model to match object in the image with their corresponding tissue label. This close model matching is what allows OVD to handle unseen object effectively. And now let's talk about molecular deep estimation or MDE, which is essential technique in our framework. MDE provides three-dimensional information from a single image, helping us better understand the spatial relationship between objects in the scene. As shown in the slide, we start with the area image, and on the left, we see the original image with traffic indicator like landmarking and clear visible. However, we use deep estimation to extra feature based on the distance rather than texture or color. The depth map on the right downplays static detail such as row marking. It emphasizes moving object like vehicle and the building. And depth estimation help to identify foreground object and separate from the background. It's focused on the depth instead of the feature. Let's introduce our overall map used in our framework. Our approach focuses on the three key steps. Deep estimation with differential object recognition, yellow world object detection, and the background averaging. And in the first part of our map, we focus on deep estimation combined with differential object recognition. First, we use deep character to generate deep maps, provide key 3D detail or scene, and helping distinguish object relationship. Next, we apply the sober filter to highlight edge in the depth maps, enhancing moving object while separating them from the static background. And we use frame subtraction to detect dynamic object by comparing consecutive frames to enhance visibility. We binarize the result and apply OpenCV file counter to create bounding box for this object. However, large or fast-moving object may become fragments due to limitation in frame subtraction. Okay. And to address this problem, we integrate Kenyan edge detection to attract object binary in the original frame. The detect edges are used to generate bounding box shown in red. We compare this to bounding box from frame subtraction. Then we calculate the overlap relation radio. If the overlap exists a set threshold, we confirm the detection as well, helping to remove false position and fix fragment bounding box. And this processing segment improve this accuracy and reliable of our object detection for further processing. And after completing the first stage of dynamic object masking, we notice a big limit in the differential map. It can detect objects that are stationary for a short period, such as vehicles stop at the red light, and this object stays still for a few frames, so the frame subtraction map can see them as moving. This can move some detection to be missed in the generate mask. So to address this issue, we incorporate yellow world to enhance detection. We can use yellow world object recognition to support a stationary vehicle that the difference map missed and detect vehicle are added the dynamic object mask. This helps show all temporary object in the scene more clearly and accurately. Now let's move on the background averaging step. This where we remove dynamic object and the reconstruction, clear static background, and the processing consistent of the two main steps. The formula define a mask M sub I of X and Y for each pixel, assigning a weight W to dynamic object and 1 to static region. This helps separate moving object from the background. For background reconstruction, we compute B's of X and Y using a weight averaging across frames. F sub I of X and Y is a pixel value in frames I, and N sub I of X and Y is the object mask. The numerator sums the weighted pixel value while the denominator normalize them in ensuring accurate background reconstruction. We use averaging because background are stable and dynamic objects show up only in some frames. This fell in missing details when object block parts of the background. It helps create a clear look. Every gene remove moving object while preserving static elements, reducing error and artifacts. Okay. After now let's moving or experiment. It's test how well different MDE map work for detecting object, and we want to see how well different deep estimation model find moving object by using deep differencing. Without deep map, object detection become noise and inconsistent, leading to failed detection. Deep information help separate static background from moving object more effectively, and deep anything outperform sober-based detection by cutting down noise. However, it has trouble with long video sequence. Flagging artifacts can lead to occasional detection error. If Creditor is a top performer, it gives stable deep estimation over frames. Plus, it has the highest recall and the detection currency. This confirms the high quality deep estimation is crucial for reliable differential object recognition. In our second experiment, we test various YOLO model. We want to find out how the quality of object mask impact background reconstruction. And YOLO V8X struggle to generate mask and lead to low accuracy. And YOLO V10X perform better, but still have some detection gaps. And YOLO V8X World V2 get the highest SSIM score at 0.96. It's made better mask and clear backgrounds. Okay, in our third experiment, we comparing different background averaging map to evaluate their effectiveness in removing dynamic object. The first approach in simple background averaging result in ghosting artifacts because the region where object appear had a high weight, making it visible. The second map used deep map difference space for object detection with weighted averaging. It performed better overall, but had issue with stationary object like car at intersection. This caused some leftover artifacts. A multi-model approach combines depth difference detection and the YOLO world object recognition. This map gave us the best result. By leveraging both the depth-based measure detection and the YOLO world object recognition, it effectively removes dynamic object while preserving static detail, producing the clearly background reconstruction. In the study, we introduced the map for removing object and averaging background is area imager. We combine YOLO world for object detection with deep estimation to achieve this. Our multi-model approach use deep difference-based object recognition. This map effectively removes moving object. As a result, it's both image processing efficient and currency. We plan to improve depth estimation in complete lighting. We will also add feature matching to cut down on background blur. Plus, we will explore 3D camera to boost efficiency. Thank you for your attention. If you would like to or paper, please refer to our full paper. Thank you.
Ma'am, do you have any questions for him?
No, I don't have questions.
Okay, thank you, sir, for your presentation.
Thank you.
Now I would like to call upon Wa Ot Siti Nur Alam to present her study on development of hybrid AI model assisted bilingual chatbot for stunting education and nutrition status classification.
Thank you, ma'am. Let me share my presentation.
Yes, ma'am.
Good afternoon, everyone. My name is Waode Siti Nur Alam. Currently, I'm a PhD student in electrical engineering at the University of Indonesia. Today, I'm honored to present my research on development of hybrid AI model assist bilingual chatbot for stunting education and nutrition status classification. This work conducted under my supervisor, Professor Riri Fitrisari, who is also the second author on this paper. In this session, I will discuss the motivation, methodology, and the result of our study, highlighting its significance in addressing stunting education and nutrition status classification. The structure of our presentation, the first one, introduction, the second one, method, and the third one, result and discussion, and the last one, conclusion. Stunting is a chronic condition caused a long-term malnutrition, recurrent infection, and inadequate psychosocial stimulation, leading to impaired growth and cognitive development. The background of study, the first one, high prevalence of stunting, and the global prevalence stunting stands at 22.3%, while in Indonesia 21.6%, and Southeast Sulawesi 27.7%. For the information, South Sulawesi, one of the province in Indonesia, and the top highest prevalence of stunting. The second one, limited access to health services. Southeast Sulawesi consists many districts and village, and approximately 80% of the population live in coastal areas. And the lack of health workers such nutritionists and health professionals. And the third one, inadequate childcare practice. For example, lack knowledge and education of the mother, parental anxiety about the children nutritional status. And then technological advancement have a significant change in various factors, including healthcare. For example, AI chatbot to improve healthcare access and quality. AI chatbot can provide medical information, for example, assist early diagnosis, facilitate communication between patient and healthcare provider. So with the ability of chatbot to operate 24/7 without human intervention and reach broader population, this chatbot offers the potential solution to overcome challenges in the traditional health system. The limitation of existing AI chatbot often face limitations such as inaccurate or delayed response, and limitation of the use of the training dataset. Okay, well, for the conversion flowchart in this study, we have two modules in this chatbot. The first one for stunting education, and the second one for nutritional status classification. Here, the UML use case diagram for chatbot interaction. We can see how the user can interact with the chatbot. For the nutritional status classification, the first step, we prepare for the data set, and then we import a library of, we use a Python program, load the data set, and then the data set processing, training the model and testing, evaluate the performance, determine and save the base model, and model deployment. Here, overall, the design of AI chatbot we propose in this study. And then to deploy the chatbot, we use Amazon Web Service and Telegram application. As we can see the figure, we can see the base model and the chatbot deployed in application. Well, for the result and discussion, the first one we use dataset from kaggle.com. In dataset, classified in 4 nutritional status, and the first one high nutrition, normal, severely stunted, and stunted. We evaluate several models in ensemble learning algorithms. For example, random forest ada boost, gradient boosting, SG boost, light GBM, and cat boost. And this figure we can see the best accuracy is for a random forest model. In this prediction evaluation result of random forest, the best model for nutrition classification, we can see the main diagonal and the figure for class 0, correct prediction as class for high nutrition, and class 1, correct prediction for normal status, class 2, correct prediction for severely stunted, and class 3 for stunted. Here, the chatbot performance testing, we use a Telegram application. We can see the Telegram can we can see in the Telegram chatbot respond the user message in Indonesia language and English context. This is classification nutrition status. When user input, for example, age, gender, and height in children, the chatbot can respond the message or the result of classification of the status nutrition. We compare our chatbot with existing chatbot like radiotherapy chatbot, ANN, and ensemble learning system. We use some aspect like accuracy, usability, accessibility, and user. Our chatbot provide highly accurate and context-aware educational response, and for real-time response, enhance to user experience, easy implementation with cloud infrastructure, bilingual chatbot, accessibility through familiar platform like Telegram, high performance on accuracy and usability metrics. For the conclusion, the performance of this study hence shown the adequate performance in disseminating information related to the stunting education and assisting the classification of nutritional status children under 5. The chatbot support bilingual interaction, Indonesia and English. This chatbot has significant potential to become health tool that supports stunting prevention education and early detection of stunting risks. And then this research has significant implication in the field of public health. For the future research will focus on improving capabilities and expanding integrating advanced features such as speech recognition, text-to-voice conversation to improve user access and engagement. That's all my presentation. Thank you for your time and your attention.
Thank you very much. Can I ask a question?
Yes, ma'am.
So you said that your chatbot is in English and Indonesian, and
Yes.
users of your chatbots are the people that are living in English language countries or in Indonesia. My question is, did you compare the results of English version of your chatbot and Indonesian version of your chatbot, or this is some general results that you presented for us?
Our chatbot, our chatbot, we try to develop Indonesia and English context because we try to implement this chatbot in Indonesia, and this chatbot can use for other countries from Indonesia.
Okay, thank you.
Yeah.
Thank you, ma'am, for your presentation.
Thank you.
Now, I would like to call upon Andrea Ogello to present their study on SFAE, Split Federated Autoencoder for Unsupervised IoT Intrusion Detection.
Hello.
Over to you, sir.
It says here I cannot share my screen until, okay.
Can you share it now?
Not yet. Okay, I think I have to restart Zoom to be able to share. Sorry about that.
It is all right, sir. We will wait for you for 2 minutes. There was some technical issue. I would request everyone to wait for 2 minutes.
Sorry about the delay.
Are you able to present your screen now, sir?
Okay, can you see my screen now?
Yes, sir, we can.
Okay, thank you. Sorry about that. So, hello everyone, I'm Andrea Ogello from the University of Palermo, and today I will present you our work on intrusion detection. So, Internet of Things devices are getting more and more popular nowadays. However, they also represent a significant vulnerability in our security perimeter of our homes. Indeed, since they have limited computational resources, they cannot execute complex machine learning pipelines to detect cyber attacks. And on the other hand, we cannot just make all our traffic go through cloud servers to try and detect attacks. Of course, there are really serious privacy concerns with that. So we have a problem. How can we detect intrusions in IoT networks without exposing our sensitive data? Currently, the centralized machine learning solutions have really bad privacy issues. So the machine learning community has tried to develop decentralized learning approaches such as federated learning and split learning. However, these cannot readily be translated to intrusion detection in IoT systems for some reasons that we'll see soon. So there is a need for privacy preserving intrusion detection system which can be run on resource constrained devices. Briefly, what we are trying to do here is try to learn the normal behavior of the network with autoencoders. And then if the reconstruction error of these autoencoders is above a specific threshold, then we can say that the traffic is anomalous, and so we flag that as a possible attack. Existing distributed learning paradigms either try to reduce the computational burden on the devices, for instance, through split learning, where part of the model is on the device and another part of the model is on a cloud server. And in that case, only the encoded version of the data is transmitted, so the raw data does not leave the device. Or and on the other approach is that of federated learning, where where there are multiple participants that collaborate to train a shared model, and in that case they exchange model weights instead of exchanging the raw data, which also preserves privacy since the data does not leave the devices, but has a higher computational burden because the entire model needs to be run by the devices. To merge the strengths of these two approaches and mitigate their shortcomings, the split federated learning has been proposed, where multiple clients in parallel do split learning on their, and then the various split models are aggregated with the federated learning approach. However, these kind of approaches are really high communication cost, since all the participants need to transmit data to the server and receive back the gradients. So what we are proposing here is a way to achieve a sort of split federated learning approach for autoencoder training that does not require all this computation. Briefly, we have multiple IoT devices. Each of them has their own data that they normally produce, which is the normal data, the one that corresponds to normal operations of the devices, and a split server that the clients, all of them as an encoder and a decoder. And then there's a split server with another autoencoder in there. So what happens here is that clients train their local autoencoder on their data. That cannot be done completely locally and with low computational cost because it's a really small model, the local one. And since it's a small model, it is not expressive enough to really be used for intrusion detection. So what happens then is that all the clients send the encoded version of their data to the server once, and the server trains an autoencoder on that. This way, the server never sees the original data, and we are preserving privacy. But it is the server can train a more complex intrusion detection system because it sees the data from all of the client, and it can better learn to represent the network dynamics. So how does this whole pipeline work when we are trying to detect if some traffic is malware or not? The input data is encoded by the clients, and then this compressed representation is sent to the server. The server tries to reconstruct the data from the client using the split part of the autoencoder model and sends the reconstruction back to the client. Then that reconstruction is given as the input to the local decoder, and the overall reconstructed traffic data is compared with the original one. If the difference between reconstruction and original data is above a certain threshold, then the client can say that probably an attack is ongoing and that is flagged as an anomaly. Experimentally, we've tested this approach on the both IoT and non-IoT datasets, and we have evaluated the receiving operating characteristic curve of the classifier and the F1 score of the performance of the classification. And we've tested this with a network comprising of 50 different IoT devices, training for 5 local epochs and 20 communication rounds in the federated part, learning rate of 0.0001 and batch size of 32. So we can see that overall this approach is quite effective with area under curve of the rock curves quite close to 1. And the And the F1 score is also quite competitive with other distributed training approaches. In particular, we compare how our system behaves compared to 2 different versions of split federated learning, normal federated learning, and a centralized approach that has all the data at once. Interestingly, we can see that in some instances, our approach outperforms centralized training, which means that the intermediate step of training first autoencoder with a lower representation power is actually beneficial to the overall performance, because that is already sufficient to detect some of the common patterns in the data. Another interesting thing is that compared to the other approaches, even if some of the clients are already infected when we are training our model, so for instance, we are deploying it in a plug and play way in a network where some devices are already compromised, we can still tolerate up to 20% compromised devices, and we still achieve F1 score above 0.9, compared to other approaches where the performance dropped quite sharply. So this is also a plus. That's probably because since multiple clients are training separately, all the normal clients are still teaching the shared local autoencoder some patterns which are typical of normal data, while in more centralized approach, we are just mixing in an indistinguishable way normal data and poison data, and that means that the autoencoder is also learning to represent patterns which should not be learned, as they are not representative of normal traffic. So briefly, we can say that this training architecture outperforms state-of-the-art distributed training when trying to do intrusion detection in networks, and this can be done at a lower communication and computational cost compared to traditional federated and split learning. This means that with this kind of approach, it is possible to do intrusion detection on IoT device with very limited resources without compromising on user privacy. And is also robust against malicious participants that try to poison the model. So summing up, we are proposing a distributed learning architecture for unsupervised IoT intrusion detection on the devices. And we can address both the privacy and computational constraints that usually prevent from adopting this approach on IoT devices. In the future, we are planning to try to explore alternative training strategies to further reduce the cost and extend this evaluation to more datasets and more challenging scenarios with perhaps a higher concentration of stealthier infected devices. If you're interested on more research by our research group, you can follow the QR code If you also would like to get in touch, there's my email, and you can contact me there. That will be all. If there are any questions, I'm be happy to answer.
Okay, just one question, quick questions. How do you define intrusion in your network? So you said the client that is not 20% what?
Okay, we assume that the traffic is characterized as an intrusion if it belongs to some categories of attacks. In particular, in the datasets that we are using, mostly infected devices are devices that have been infected by some sort of botnet virus, so they are engaging in DOS attack, DDoS attack, and or doing some other data exfiltration attacks compromising the privacy and security of the network.
Okay, thank you.
Thank you, sir. Now, before we reach the end of the session, I would like to give one last call to Smita Mehendale or any of her co-authors to present her study. If any one of them is present here, please let me know. Okay, all right. I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 10th version and all the previous 9 versions of the conference. We will be happy to have you in the 11th version in 2026. All the presenters will be getting their digital certificates through email within 2 working days. Further, all the papers have already forwarded to the Springer. The publication will be live within 6 months. Kindly cooperate with the team of ICICT 25. I also thank our session chair, Professor Renata Mekovic, for chairing this session. I'm extending a token of appreciation on behalf of Team ICICT 2025 and all the presentees that were present here, along with the Research Foundation and partners. Ma'am, I would request you to share any closing remark you may have for the presenters today.
Thank you very much for inviting me to be session chair. Also, I would like to thank all the authors for sharing their project results, and I wish you all good luck in your future researches.
Thank you, ma'am, for your valuable presence. And now, as we reach the end of the session, I would kindly request everyone to switch on their cameras for a quick snapshot of the virtual conference. I repeat, everyone, please switch on their cameras for 1 minute, please. Okay, thank you, everyone, and have a great day ahead and take care.
Thank you, ma'am.
Thank you.